We can start it now. Participant, good afternoon. I welcome you to this second session for today's FDP. For this session, we have Dr. Tiwary sir, who is currently working as assistant professor in Department of Metallurgical and Materials Engineering at IIT Kharagpur. Uh, he did his Bachelor's of Technology from NIT Durgapur, then PhD from IISc Bangalore, and he has also postdoctoral experience from Rice University, USA. His research area includes development of two-dimensional materials and composites, development of porous and ultra-low density materials, then bio-inspired composite and innovative materials and 3D printing. To his credit, he has almost six international patents and one national patent. Along with that, he has around 250 publications with citations nearly equal to 5,000, and H index is more than 35. He has many awards to his credit. To name a few, it is Excellent Microscopist of the Year by Electron Microscopy Society of India, Young Metallurgist of the Year by Ministry of Steel, Government of India, and many more. So we are very much thankful to you, sir, to kindly accepting our invitation within a very short span of time and sparing time from your busy schedule and putting forward your expertise to this particular faculty development program. Sir will be talking on 3D printing opportunity and challenges. So on behalf of Department of Production Engineering, VSCCT Burla, on behalf of the entire participants, as well as of my own behalf, I welcome you, sir, to this session, and I request you to kindly start the session. Please, sir.
Okay. Thank you, Dr. Mahapatraji. First of all, thank you for the organizers. I hope I'm audible.
Yes, sir. Yes, sir. You're audible.
Okay. Okay. First of all, thank you. Thank you for giving opportunity, and also thank you for giving this. It was in short notice, but it's fine. It was in short notice, but when I saw that little bit about, I get to know about the whole program and what you guys are doing, then I thought it's although this virtual meeting and conference or this kind of seminars have its own challenges, it's always not that easy to interact, because even we are doing classes and so on, and we have to have several challenges. Yeah, it will be nice if we can meet and I can show you real printing or real things happening, but unfortunately we have to restrict ourselves to just the presentation and talk. But what will be the best way is, let's make it more interactive. Okay, and I don't want it to be like monologue and then I continue saying. I'll speak for half an hour, okay, and then we'll wait for say 5 minutes or couple of minutes, and you guys can ask questions. Like if you have any question or any comment or you want to discuss, we can have a short break for a couple of minutes, and then again we'll start. Okay, so the whole 1.5 hour we'll have 3 subsections, and we can go a little slow. I have tried my best to put more realistic and more research related things, because I saw previous talks have covered basic concepts and most of the basic things are done. But what I have, if you look, my talk is organized in such a way that we can, because most of you are already faculty somewhere, or you're doing, you are intended to get into this 3D printing research area. So the whole talk is organized in such a way that you can get to know that what's going on currently and what are the direction which we are working, or in general the community is moving. So with that, let me share my screen and then we can start the presentation. Okay. Okay. Is the screen visible?
Yes, sir, it is perfectly visible.
Okay, great. So the title of the talk is, as already told, that 3D printing opportunity and challenges. Uh, you know, if you look at the industrial revolution, right, this whole thing started, and what I feel is in human history, there are certain milestones uh, which are really, which has changed the history of the society or history of mankind. And one of them, certainly, which is the closest one is industrial revolution, right? And whatever we see today has lot to do with this first industrial revolution, which started in Britain. And if you go back to your history books and you read about it, and what we see is still this industrial revolution. There are several countries who were leading in their own areas, and they were in top of production or productivity or yield or whatever economic measure you say, they were on top. But what happened, this first industrial revolution, which started in Britain, what they started doing is started bringing machine into production. And as a result, if you see the textile industry, which was one of the major industry at that time, where Indian or any other countries were making cloth or any good, textile goods with a lot of manpower, lot of cost, and also it doesn't have a lot of freedom to do things. Whereas industrial revolution can start making things much faster because of machine. At the same time, the reproducibility, like doing same thing or same size of those things, or standardization was much better. Optimization of the man plus machine plus resources were well optimized. And after that, if you see the countries who really take over this industrial revolution are leading till today. Now, and the next revolution which came was in car industry, right, which automobile, and which was started with Ford. And what he says, based on him, if before Ford was one of the initial company which started making cars with customization of car, they call it. Otherwise there was only you make a car and then just it's going to have one particular thing. But then this company, they started making car with a different color or different requirement. And then after that, you see in automotive industry, and again, automotive is one of the major industry in all across the world. The countries who are making good cars, or they are manufacturing cars, are having their much bigger share in economy and so on. But I think the credit, what his perspective was that, okay, it's not just car, we have to make this car based on individual customer or individual taste and so on, and that revolutionizes the automotive industry. And that's what when I say customization means, the old cars used to be like that, and then if you see today's car, it's kind of everywhere. And that's kind of second industry or second revolution in industry, we can say that. After that, if you see, every goods today has several of categories, several of partition, or what you call categorization, that you want X size, Y size, X color, Y color, and so on. But at the end of the day, the number of opportunity or number of option become quite common. Like giving option become quite common in any goods or any product as such. Now, the third revolution, and which is in the process, is manufacturing. And again, we are coming back to the same first industrial revolution, I think, where the machine were introduced. Now what we are talking about, can we start making things without even human? Can we do things with with automatic and so on? Now, in manufacturing, in general, I mean, most of you know there are two methods. One is additive and other is subtractive. Now, subtractive is very conventional, and I think everywhere it's there, and every college or every industry, they will have some bits of this kind of subtractive manufacturing, where drilling, milling, turning, and all these are there. What you do here is you cut the block into required size and shape or dimension, and throw rest of the material and give a shape of whatever you need. But the problem is, remember, when you cut this, you lose a lot of material first. Second, these are really time consuming. Okay, but just because there was no other opportunity for till now, people were continuing doing it. But now this word called additive manufacturing came, and the word itself called additive means you add things rather than removing things, and it brings a lot of exciting things and a lot of opportunities and a lot of challenges. We'll go first talking about opportunity, and then we'll come back to challenges and what are the limitations in this whole area. Now, definitely, when we bring additive manufacturing, you can make 3D objects by adding layer by layer, or manufacturing layer by layer, and so on. Or depending on what kind of tool you choose, you can make in different speed, you can different resolution and different material. All these can be done. And in the right, you can see some of the very complex shape. If you want to use conventional method, it can take very long, or you cannot do for every material. But with the 3D printing, we can do all these things in a very less time or very efficiently as well. Now, I think this slide is kind of not needed now, because I think everyone told about layer by layer and so on. We are not going to talk about it. Now, if you look at manufacturing decision, the three important things which decides the whole manufacturing is speed, price, and quality. Now, if you really want to have a perfect combination, you need to move in between somewhere here, where you have a lower price, higher speed, and acceptable quality. Now, if you look at 3D printing, the good thing is it gives you freedom to tune all of it up to a huge extent. And definitely speed is one of the way where you can do much faster. Quality wise, yes, you can tune the quality, or you can reproduce it and you can make the same thing and again. And price is something which is optimized, or which need to optimize depending on what process you are choosing, or what material you choose, or what you require, and so on. But definitely 3D printing gives you flexibility to check or choose any one of theirs. Now, let's quickly go to advantage and application of 3D printing, so that I'm sure previous speaker have talked about it. But what I have tried to do is I have just tried to categorize different areas, so that we know what are the avenue, or what are the future direction of 3D printing people are looking at. And the first is design. Okay. Now, till now, if you look around things, if you make by a normal conventional manufacturing methods, it used to be simple or well shaped. But when it comes to 3D printing, now you see in different area of in either research, manufacturing, or utility, or even society, or even architecture. Now we started looking complex shapes or complex structures, and people started making very complex shape, which was unimaginable till we had never had this 3D printing. Now, the first thing is, yes, you can create complex shapes and part. It can create geometries and also allow large amount of freedom. You can decide how you want to make it. Now you can make a single piece, or you can make multiple. You can repair them with the 3D printing itself. Or remember, when you are doing this 3D printing, you don't need to make in parts. Generally, you can make the whole block and you can use it. So these are the very basic advantages in terms of complex structure. Apart from that, that brings us to next step, where we can personalize or customize manufacturing. When I say manufacturing, what I mean, suppose you want to make jewelry, right? And remember, everyone wants to have their unique jewelry, or you want to make for education purpose, or even for medical and so on. So what I mean to say is, if someone wants X in 3D printing, that can be customized with much less expensive, more flexibility, and with a reasonable speed. Now, as we discussed, when you go to this subtracting method of 3D printing, subtracting method of manufacturing, one of the biggest challenges is tool, right? So suppose someone wants to craft things on metal. the tool gets eroded or breaks very easily. Whereas when you want to, when you're using the 3D printing and so on, there is no concept of tool as such. So then, remember, then the whole planning and whole designing, which was in production, goes in designing tool, is no more required. What you need is just choose the method of printing, and you can make anything and everything with all flexibility and all ease, all comfortness. Now, yes, people keeps on talking about 3D printing in terms of market, right? So if you look at, uh, for example, you come up with a product and you want to put it in market. Now, one of the bigger time goes into scaling up. When I say scaling up, what I mean, suppose you make a prototype which is, say, inch by inch, and really you want to make the real product which is 1 feet by 1 feet, maybe 12 times, and you want to scale it up. Now, in normal method, it's not very simple because it involves several of optimization. It can have a lot of defects. It can have a lot of challenges involving into it, and all these takes a hell lot of time. And that's where the longest time into the development of any technology or any good really goes in. They have to spend time on that. Whereas in 3D printing, the nice thing is, if you choose printer and the scale of printer, suppose you take a real laser-based printer, you print something of inch, or you make it foot, the scaling effect is not much because you are using the same technology. It doesn't involve too many tools or too many parameters which need to be optimized. So that reduces the development time drastically. And that's one of the way why people, if you look at number of startups or number of companies who are growing faster in this startup business, are quite a bit of them are on 3D printing, because the moment you produce new class of 3D printer and everyone is looking for it, they start using it and so on. So the flexibility or the speed of the flexibility to consumer, at the same time flexibility to scale it up, really makes it one of the key development in, I think, in last 10 years which has happened. Yes, as we told already, it has less waste, sustainable, environmental friendly, and all these are advantages, because if you, and most of you have done this conventional manufacturing or subtracting method, where you create dust, and if you go to the places where people are working with clay or working with ceramics, while doing cutting, they really generate huge amount of dust and so on. Whereas in 3D printing, what you do is just print without any waste first. Second, you don't generate any dust and those kind of things, which makes it much cleaner and much environmental friendly. At the same time, sustainable. Generally we don't think about sustainability, but if you really think suppose you have a material or metal or any good which is of limited resource. In such cases, suppose you have 1 kilogram of gold and you want to make things, and if you use a method where you need to cut them and again do it, again there is a loss involved. So you start losing them. Now, if you have a 3D printing method where you don't lose even a gram, that makes it more sustainable. Then what you can do is you can keep on making things, and if you want to, because the losses are low, definitely it helps into retaining the material and utilizing the material in a better way. Now, limitation, yes. There are few limitations. One is higher cost initially, right? So again, depending on what method you choose or what scale you're talking about, definitely it has higher production, or also depending on resources, it can get little costlier. But again, if you start doing for very long, that can be optimized. But that is something people need to think about, and that people are working on it. Currently, because this is the area where things are just started in last decade. So yes, we don't have too many material choice. So someone can come and say, can we print diamond? Or you can come up and say, can we print carbon-based material? Just those things are not there. Not every material can be printed, or you cannot get every color and so on, because people are working on it. So we don't have all those options at this moment. Yes, strength and endurance. One of the initial talk I heard that yes, people try to see how we can match the strength-wise. But again, with all limitation of all optimization, we can achieve it. But that's need to be done. That is something which need to be done in any 3D printing of either method or any material. Accuracy of printing object is depending on which printing method you choose. The surface finish or the dimension tolerance is still one of the things which, if you are really talking about precise dimensional, the shrinking or expansion and so on during process is still something people need to work on, or also surface finish is something people are working on it. And if you look at the market printer, this is currently, because not too many industry, like people, all the industries are putting 3D printing as a future perspective. They are looking how we can, kind of start doing things, but still it's not really in the market where they are producing large quantity of goods using 3D printer. There are small things it's been done, but it's not universal yet. So we don't have too many large scale printer. Most of the printers are of limited size. So that is something which people are working into. I think just quickly brief history, and not because most of the speaker before me, they have talked about history of printing, but I just want to spend 2 or 3 slides on it, and just to give you perspective why this whole 3D printing all of a sudden came. People can talk about, oh, 3D printing, if you really understand basic science-wise, I think it was there for a very long time. And it's not something we just came out of blue. What has happened with time, and that's what we are going to discuss, what changed in time that this whole 3D printing boom came up. Now, if you look at the history in 1983, a group of physicists or group of scientists, they were making stereolithography. And it's nothing but making a material. You make first layer and then let it cure, then put the second layer, let it cure, and keep on doing it. They call it stereolithography. And they put the short name SLA. The patent was granted and so on. Now, and this is the the news which came all over. If you see background, and one of the very important observation you can make is, you see the complexity here, right? You see how each of these wires and so complication was there. But the point is, they were able to make a small object in 1986 or 87 with this whole science. But nothing happened, or not major development happened in almost 20 years, right? Or I'll say 2 decades. Nothing was happening. People were like, it was going in research and people were doing it. But the real boom started in 2000 or 2000 or 2003 onwards, where this started becoming one of the buzzword. Now you can see interesting observation, right? A lot of science which has been developed before, which never came into real notice, just because resources were not there. When I say resources, the first thing I refer is computers. Okay. Now, computer or electronics or computer human interface was not well developed till 2004. So, although 1986 they developed everything and the science was known, but it took almost 2 decades for people to really develop the computer thing. And once we started getting computers, or the interface of computer and machine, they reached to a level where they can really make it easy. And just because of our computer capacity today, or the software to control motors, or the real machines, we are able to make these printers in home or anywhere you want to do. You can do it. Even small, your laptop or mobile phone nowadays also. So one of the printer we have, you can print using mobile phones. So the point is, with the computer development, people started realizing the power of 3D printing. And then this whole history follows, which people talk about all over, and it's there wherever you go. In the history, another development happened. See, although 2005 and 2004, the second 3D printing or the real 3D printing boom came up, but till 2009, it was still into the very initial stage. Not too many people were working into it. It was limited to a very small group of people. But after 2009, the first 3D printer was built, and then you start seeing every year more than 200, 300 new 3D printing company comes up with their own innovation or with their own area of expertise, and that continues. And any country you go, if you see the number of successful innovators or incubations are in 3D printing direction for sure. But still, there are several things which can be done in the 3D printing area in terms of research, and we'll talk about that in the subsequent stage of the talk. Now, as we talked about, as I told you, application area, automotive industry. Yes, India is one of the good car or I'll say lead in car making or car consuming. Also, we have a huge market. But remember, still in car, you need a lot of customization, right? Suppose you want to make things for specific, or you want to make high-speed car for very specific dimension and so on. So automotive industry is one of the driving forces in the 3D printing area, and people are working in really with a very high speed in this direction. Just for example, if you go on news and you find people have developed, or they claim they have developed, and it's all over in the news, 3D printed tires. Now the question is, why 3D printed tires is needed? The first thing is, suppose if you have a road, and it's very common in India that we get the tire puncture. Now, if you are moving with a very high speed, what's going to happen is, you end up having a huge number of accidents. And yes, we do have a lot of accidents because of such cases. And in West, it's bigger concern, because if your car is moving with a very high speed, a small puncture can lead to a big disaster. So there are a lot of work going on in this direction, where people are trying to build it up so that we don't face those things. At the same time, if you have a 3D printed tires, you can also take care of the roughness of the surface. When I say roughness, means if you have a small ups and downs, those can be taken care of, because these structures are built in that way that it can take care of small shocks. So that helps in taking care of the body of the car and so on. But that is one of the direction people are working. There are a lot of things need to be done before you really see. But yes, there are initial success as well. Medical industry is one of the really driving force in this area. And I think tomorrow you have a talk by Professor Vikramjit. I'm sure he's going to talk about this kind of advancement. But yes, medical industry, the one thing is, we have to clearly understand every human is different, and each of us, although we have a medicine which is for generic, but if you want to have implants, or you want to have a operation, or organ, each of us have their own, our own characteristic into this body, right? So what happens if you look at your bone, or any dimensions, so on, they are very specific. Now, if you really want to repair things, a universal part cannot, although people try to use it, but it's not very sustainable or not very comfortable. Now, if you really want to get rid of this part, the only solution can be 3D printing, where you can scan the body parts. And you can just give an example. If you go and if you undergo any accident, if your bone breaks, what they do is they put metal parts, right? Now remember, these metal parts are not custom made, they are very generic. So when you put it, and after some time they need to remove it, because it's going to create a problem for you. Now with the current technology, people are trying to make this kind of implants, which is very sustainable to your body. At the same time, it matches with your dimension, and so that you can fit in very perfectly, which will help you in terms of healing. Also, it can help you in sustainability of your body as well. Yes, prosthetic is another area where, again, each of our body dimension or features are different. So with 3D printing, we can build things like that. Like, for example, the leg, where you can choose which part where you got infected, and you can make things like that. If you have a small ankle or a small twist and so on, you can take your shape and print and make things of your dimension. At the same time, you can create porosity. It means you can create lighter weight, easy to wear, and so on. In one of the research area, we'll talk about that as well. Yeah, dental is again part of medical. Again, I think people have been doing this thing, but it was, if you go to a dentist, they do take the shape and takes longer, but with 3D printing, you can do faster, and that can help in this industry. Aircraft, yes, aircraft aviation is one of the industry where reducing weight or increasing specific mechanical strength or specific modulus is a key issue. With the 3D printing, definitely people are sure that we can improve this whole efficiency of fuel in a drastic way. But we have to remember that again, this is an industry where the risk factor is very high, and that's one of the things which concern them. But still, people are trying to go in this direction. There's a lot of work happening because remember, all these aircrafts does have very complex shapes. And if you I'm sure you guys are taught about this, that making complex shapes like this in aircraft, it takes very long time. With the 3D printing, people are expecting it to reduce that, and also you can tune it very easily and so on. But again, this is an area where people are doing a lot of research. Entertainment, yes, entertainment is especially with the movies are getting expensive and people want to see more realistic stuff or more realistic looking things. People wants to have their own way of imagination, and entertainment is a way in the place where you really create things which may not exist and so on. 3D printing is used drastically all over the world for this business. Art and design, yes, you want to see beautiful things and you want to have this kind of complex shape. 3D printing gives you whatever you want, and that's one of the area where I think it has taken a huge lead already. You may or may not know there are several things which comes to you which are already 3D printed. So this is one of the area which has taken way ahead, and they are doing very well in this direction. Architecture is another area where it's moving very fast, because if you look at old buildings here in the background, they're like square shape or cylindrical and so on. But what people wants to see is something like this. And that has started coming, and in several parts of the world, they already are doing this 3D printing of buildings, where they make this complex shape first easily. It's easy to make. At the same time, you can decide how much complexity you want, or you can customize. But this is the area where I think it's showing with depending on infrastructure or utility or requirement. But again, this is somewhere people are moving very fast. Jewelry, yes, as I told you in one of the initial slide, that if you have customized jewelry, you want to have customized or specific, and with the 3D printing, they are able to do. There are several companies or several groups who are trying to do this kind of customization of jewelry. Education is one of the another area where 3D printing is contributing in a huge way. If you remember in your school days, if you have taken biology in your 10+2 or even in your bachelor's, you end up cutting a frog or cutting a species. And some of us may not like it. It was really kind of, if you are not very, what you call, if you can tolerate those, I think brutality, yeah, maybe you can say brutality. If you can tolerate that, you're okay. Otherwise, you can, some of us can faint and so on. But the nice thing about 3D printing, you can print any object, whatever complexities. You don't have to kill anyone. You don't have to cut frog and then stitch and throw and so on. You can easily learn all those things, especially for human anatomy. In medical science, this is very useful, where they 3D print the parts, and then you can teach the batch by batch, and you can use it for several years, and still you can learn things. So 3D printing, not just in medical, also in any other science area, it's coming up very easily. It's already there in the market. You will find a number of examples of this. With this, I'll quickly take a 5-minute question or 2 or 3 minute question if you have, then we can proceed. Any questions so far? Okay, so what we'll do is, as we are running a little late, I'll proceed with it, and maybe we can spend time on question answer thing. So, having said all these things, let's come back to today's world in terms of the nice plot, which is called expectation versus timeline. Okay, and here what we see is different kind of technology which has what you see around you. And let's understand this curve. So expectation versus time is a very interesting plot where for any technology, what happens once it develops, and you can see my laser pointer, right? Hello?
Yes, sir.
Okay, perfect. So if you see any expectation versus time curve, what happens as the technology comes, it gets hyped. And this is what it shows in the curve, that steep increase. What it means, in less time, the expectation rises very fast. It means, oh, it can do X, it can do Y, it can do Z, and it appears that this technology can change everything. And then it comes to a peak where I think the technology has been projected enough that it can do almost everything and it can meet all the expectation. And then comes reality. When I say reality, it means people started seeing, oh, you start building things, okay? And then you started, oh, there are the limitations, these are the problem, and then this, if you see expectations start decreasing, oh, it cannot do this because of this limitation, or it cannot do that with that limitation, and so on. So the expectations start decreasing. Okay, and again, this curve changes depending on the exploration. Sometimes, if not too many people are exploring, it can be a little bit flat. But if the expectation is high, this curve also follow the similar trend, because again, a lot of people put money, a lot of people put a lot of resources, so they realize this whole problem comes here. And then comes to this particular point. And this is one of the interesting point where like people realize what is the real utility of the whole technology. And from here, people start developing things or try to modify or try to tune or engineer the whole technology so that it can start filling or start solving the problems, and then it takes off, because now commercial things will happen, a lot of company will come up and it will start taking up, and then it follows the trend. Now in 3D printing, if you see the consumer 3D printer, when I say consumer means what is there in your lab or even in company, this is where they lie somewhere around here. Okay, and then if you see more industrial thing, printers are already which are in use, they're already here. And the nice thing is in 3D printing is both of them are 3D printing, a part of 3D printing. But yes, what the nice thing in terms of marketing or the people in finance, they clearly see in 3D printing, yes, there are a lot of things nice happening, although there are challenges. So this is a nice technology where both things are happening. And apart from that, you do see several other things like bioprinting and so on, which is still into this area or in some of this area already reached. But again, 3D printing as a combination, it works in both the direction. And remember, this is data of 2014. I think in last 5 years, it has moved quite a bit in both of these cases. But yes, this is one of the interesting way. So what we are going to do is we are going to, in terms of research, we'll still, we'll still discuss this particular area. And the industrial people, they generally talk about this. In my talk, I'll concentrate in this particular printing area. Now, again, these are another two interesting plots which we need to see really in a realistic sense. Now, if you have a complex part, and this is the fabrication cost, right? Now, what happens, and this particular plot is for traditional fabrication, and this is for additive manufacturing. And this is an interesting plot just to understand that if you see, if you want to make a simple parts, right? Now, the cost for traditional is lower than additive manufacturing. So someone comes and say, I manufacture 3D printed pipes, definitely it's not going to be that exciting or useful. But now as you keeps on increasing complexity, you can see that traditional manufacturing, traditional fabrication is going to become expensive. Whereas additive manufacturing, it is going to be almost similar, or the increase is not going to happen. But the most interesting part or most interesting advantage of additive manufacturing is this area where traditional fabrication cannot be made. And that is where I think additive manufacturing can take the next leap, because something you cannot make or you cannot imagine, additive manufacturing can give it to you. And this is where I think most of the research is going on. Now, different methods of 3D printing is already discussed, and I think people have talked about all the methods. Depending on who has categorized it, it changes. But again, depending on material or depending on society, there are several of these this 3D printing tools and technology. Just to give you perspective, every method comes with some advantages or some disadvantages. Now, that's something which you have to make balance of it while doing any 3D printing. But in terms of research, we'll try to see where a researcher can get in and what are the things we can do. Again, for example, if you have an FDM-based printer, which are very simple, it doesn't use any toxic material. It can be kept anywhere. It doesn't need any post-processing because it has a lot of nice surfaces and so on. It's cheap, hence it can be easily carry, or you can move, it's light, and so on. But again, it has limitation, like the accuracy cannot be completely depends on the filament. Again, the filament you cannot make of any material, so that's another limitation. And in general, remember, these are made with a low temperature polymer, hence they are not very sustainable at high temperature. Also, the strength is, you cannot make really big structural material and so on. So we can go on, and having each of these tools, it can has advantage and disadvantage. Depending on which tool you choose, you have to live with it. Now, I think all these are discussed already, and we will not spend time on it. I think in one of the last sessions, someone asked the question about it, and I thought it's good to put this slide. In metal, and especially in manufacturing, this laser-based printer is all over, and you see every manufacturing company is buying it, and they're trying to see how we can replace the component. But there are few challenges which are kind of crucial in this metal-based printer. First is porosity. Okay, whatever method you use, whatever printing you use, still people are trying to see how we can achieve 100% densification. Now, remember, if you make the component for space or for atomic energy or things like that, and you are supposed to make a solid object. Now, if you have a very small porosity, and material scientist or mechanical engineer will agree with me that even a 0.1% porosity is good enough to have a catastrophic failure. When I say catastrophic, means suppose if you have a void, and which is going to act as a site for crack, it's going to expand all over. And as a result, you cannot really put things in space, or even in nuclear energy, or even in for that matters, for very specific medical case as well. So you don't want those things. So achieving that, it's still a challenge, and people are working at it. And isotropy is another thing which is very crucial in most of these 3D printing parts, because if you change the direction of the object, you see a difference in mechanical property. Yes, and if you look at horizontal versus vertical, the porosity changes, which is completely which is not very easy to control. People are trying to do and try to see how we can do it, and at the same time you see a huge difference in directionality in terms of grain size and so on. So that is still an area where people are doing it, and a lot of metal-based 3D printing is still concentrated in that area. Yes, it has. We discussed about some of those challenges and so on. I think we don't need to discuss anymore. One of the risks which is coming with the 3D printing is intellectual property. When I say intellectual property, what it means is, if you remember, you want to make a parts of any object, and the patent used to hold with X company because they have the technology to make it. But with the 3D printing, anyone and everyone can make things. So in this case, there are a lot of companies who hold intellectual property. They are worried that how to kind of keep track of it or keep hold on it, because all those are going to be, any parts can be made by 3D printing, so they may not get those things. Yes, cyber risk is there, and a lot of discussions are in this direction. But again, that's something which for every technology it comes up. Liability is another thing. Suppose you do 3D printing parts and then it fails somewhere. Now, trying to understand where it fails or how it failed is something which you cannot, put someone. It can have a number of reasons. So again, if some damage happened or some failure happened or some bug happened while processing, you cannot go on computer and blame him. You have to kind of, you have to live with it, and you have to see how you can change it. But again, this is something puts a lot of legal thing into a problem. Yes, space is something which is again A lot of complexity comes into picture with 3D printing. People are really worried about how to preserve it or how to manage it. But yes, that's another challenge. Just one or two slides on about this particular thing, which is uh, I think it's a myth, and people, whoever is not part of this 3D printing, they will have this kind of notions. And I thought it's a right platform to put this. For example, people think that 3D printers cost too much. Okay, now, for example, if you go to a place and say that, oh, I work in 3D printing area, and then the first question comes, oh, you must be having like 1 or 2 crore of project, and you bought like a lot of big equipments and so on. Just to make it clear, if you say 3D printer, it doesn't mean 1 or 2 crore equipment. You can buy a 3D printer as cheap as $100. And in India, I can tell you, like, there are, if you go on websites or online, you can buy a polymer-based printer almost as a cost of, say, 20,000 or 25,000. A reasonably good quality printer, you can get it, which you can use it for research, or you can use it for your work. So it's not every 3D printer is expensive. Now, another thing comes at, oh, 3D printing only done for plastic. But with the 3D printing development in just last 5 years, you can find, or you can just go on web and you can see anything and everything can be printed in today's world. And not just that, people have printed things like wood. People are printing things like food and concrete and so on. So it's not just limited to plastic. You can print anything and everything just depending on the method or the printer you have. Now, it's very, you'll find all over news, and someone comes and say, oh, we have printed organs, and X university or Y university has printed heart or lungs and so on. But the reality is, yes, all these are done, but all of them are at lab scale. Again, there are a few places you'll find this claim that, okay, they are using and so on, but still, I think in commercial level or in the reality, we are not there in terms of printing organ. Now, again, people think that 3D printing is like quick, right? People think, oh, 3D printer means it's like a paper printer where you put things and immediately it comes out. But in reality, yes, 3D printers are fast, but it's not, it's not like your 2D printer where you can just do in a minute. It takes time because it does layer by layer. Now, another thing which is all over in news or all over in social platform, that 3D printer soon, every house will have 3D printer and so on. But the reality is, in several of school also I have seen people buy 3D printer. But again, if you have a 3D printer and you don't know what to do it doesn't serve the purpose. So anyone who buys 3D printer, they must know what are the requirements they have, what are the things they want to do, and what you can do and what you cannot do, and where to utilize. All these things should be clear. Otherwise, it's just going to kind of waste your money or resource as well. Okay, and again, this is something which we discussed already. People think that if you go and say, oh, this is 3D printed, so people expect it to be very cheap. But the reality is, no, 3D printer does involve a lot of things. For example, technical manpower and several other things. So remember, it's not as cheap as we think. Yes, if you make it large scale and you're making multiple of it, you generally come with the economy model where you can recover. But the reality is, not every part is cheap. Again, 3D printing is for large manufacturing. This is another myth which is all over. People think that 3D printer parts need to be big. The reality is 3D printing is very popular in small size, because in a small manufacturing, if you try to do conventional methods, then it becomes very expensive. Suppose you do make samples with a cutting or CNC with a very precise tool and all, they become very expensive. Whereas 3D printing, if you can do precise, or you can control the precision and size, that can be useful. Now, yeah, so these are the things which we already discussed. And one of the development in terms of material is we can print multi-material, we can print multicolor, we can do faster, we can do easier. Any structure which you put into model, you can print it. You can do innovation in printing. You can do improvement in structure, or you can topology and all these things. You can 3D print big structure like buildings and so on. And if you develop a new material, yes, you can do 3D printing of it. So these are the direction which we work in our lab, and I'm going to talk about all these things in subsequent slides. yeah, these are the example of multicolor printing where you can print each of these parts with different material. Metal printing can be done with a combination of materials or alloys. You can choose some of the material which you cannot join by conventional method. With 3D printing, you can, like for example, you are doing force joint and so on. Those can be done while printing. Buildings, yes, there are several examples. We can print complex buildings with a combination of different things, not concrete alone and so on. And yes, there are a lot of examples where you see these cars and these kind of parts are printed, and you'll see in any ASME or any engineering meets, these are shown there that you can print the whole car with just one printer. Now, just in 2 minutes, we'll quickly brief about how really any 3D printing, what are the steps you need to go. First, you need to create a computer-based model, which is you need to print, and there are a bunch of software which you can help us in doing it. And I think in my previous lab visit or lab discussion, I saw they were described it. So you need to create a computer model. Then you need to create the file, STL file, where the coordinates and so on are mentioned layer by layer, or the coordinates which your machine can read. And then you put them and check, is it consistent? You have a hole or things like, you have a defect or a small porosity holes and so on are there. Those things need to run, or you don't have any bug in the printing. And then you put this solid or your proposed model into the computer and connect with the 3D printer, and see your control of the printer is connected well with the computer or machine, whatever computer machine you have, and then it start printing. And these are the only major 4 steps. And then removal, once it's printed, there are different methods of taking it out. And some of the cases you need post-processing, some of the cases you don't need. So these are the 7 basic steps any printer will have, and you have to just first 2 steps are generally common for any printer. The only change is here, setting up device and control, and printing is what changes, but other steps are same in most of the printers. Now, so this is what I discussed quickly about 3D printing area. Now, what I'm going to talk about is what I do in the lab. Now, as when you go to join as a new faculty in any place, or even you want to start this new area, generally what we do is we choose the when I started, what I did is I choose a simple area where without complexity we can contribute. Now, and being my background in materials or metallurgy, I know about how to strengthen material. Now, if you see the figure A, which is compressive strength versus density, and Ashby is the one who put different class of materials into a sort of map. He mapped all these regions for different class of material. For example, if you have foams, and foam does have woods and honeycomb and so on, all these also fall into a subset of this. But what you see here is all these material have lower density, and they have lower strength as well. When you move next, you have a plastics where you see the density is little higher. At the same time, you get strength also higher. Then comes metal and alloys, which have much higher density and a good strength. And then ceramics, which is on top, which has reasonable good density and good strength as well. And in between is composite, depending on which is your matrix and so on. But the interesting part in composite, you can change the variation in the density is not too much. At the same time, you can see a huge increase in strength you can achieve because of interface engineering or different methods you can do it. But if you really want to have a material for any application, the ideal material should lie in this range. When I say in this range, it means you want to have lower density and higher strength. Now, there are several metal and alloys. They do a lot of hardening mechanism, strengthening mechanism, and so on. But the problem is the achievement, whatever the improvement you achieve, you can achieve higher in strength. For example, I take a titanium alloys, which is shown here, and you can see, suppose pure titanium is here. Now, if I put a lot of hardening and a lot of methods of treatments, of processing, even it can be composition, what you can do is you can increase the strength in vertical. right? But what you see is the density is not much changed. So you can have a variation in density, 1 or 2 or maybe 5%, but it cannot be drastic. At the same time, for example, steel, aluminum, all these alloys or material, the difference is very small. And the reason is all these are because you change the lattice structure or change things at atomic level. But in nature, nature choose, if you look at things around you, they do change the topology. When I say topology, it means they give curvatures, and we are going to discuss more detail about it in subsequent slide. But if you change topology, you can improve drastically. At the same time, as we were discussing, density is one of the biggest problem in metal or structural 3D printing. Now, what we decided is if you really want to utilize the current 3D printing, why don't we start printing porous architecture? Now, the moment you start doing porous architecture, the first thing is you can reduce the density drastically. Now, if the porous material with much lower density can have a strength, then we can really make architecture or materials or composite in this range. And that is where the whole research we started. And if you want to divide this whole topology engineer architecture materials, there are different category. One can be microscopic scale. It means you make a porous material which is macroscopically big, or you can make porous molecules. Means your material itself is such that it's porous at molecular level. Hence, you get very small nanoporosity. Or you can choose nature-inspired structure, and we are going to go through some of the example where we take nature as inspiration and build this architecture. Or you can generate mathematical-based model. Mathematics is really beautiful, and someone can utilize it, and we can create a beautiful architecture. And we have shown in some of the examples that we can choose some of those, and we can 3D print, and it can give a lot of exciting results. Because of time, I cannot discuss all of them in detail. So what I'm going to do is I'm going to give you a flavor of all these. And if you have question, or if you are interested more, we can discuss in detail, or you can drop me an email later. Now, first example is sea shell. Okay, if you go around any sea beach area, what you see is you see a lot of these shell structures. And remember, there are a number of sea shell shapes. And if you go, there are different museums in the world where they just keep all the sea shell structure and so on. Now, one of the thing is, if you see the sea shells, none of them are simple shape. What you see things around you, they have much complexity and so on. Now, in nature, you don't find things simple. Like you don't find things of cube or rectangle or cylindrical shape. They are really complex, and you can see. These are the picture from Grand Canyon. You see this kind of topology you see all over. You can see shapes all around which are not simple at all. Now, nature make this topology or this complexity for some reason. And in 2014-15, the question which I was asking is, even why nature choose this kind of topology? Can we understand it? And the first we took at this sea shell structure. And there were work already at microscopic level. When I say microscopic, what I mean is they took the sea shell, or which is nickel-like structure. There are a lot of work here, and they break them. And what they see is they're nice plates of ceramic separated by organic layer. And just because of this kind of architecture, you do get much higher combination of strength and toughness. But if you look at nature, these are at nanoscopic level or microscopic level. You can see this length is 20 micron, and each of these plates are around a couple of microns or half of micron and so on. But these are at microscopic level. But if you go around in mountains and so on, you do see very similarity. And remember, these are meter thick. You do see a ceramic layer of deposition separated by organics in between. And that also gives it stability. And these structures are stable for ages. And some of the places you can see, although there are erosion, but still they can take the load, or the structure can be stable. So the idea is, okay, if you have something at nanoscopic or even microscopic, the mechanism or the mechanics does have a role to play. And what we started understanding, the first work we did in 2014-15, where we took the sea shell structure, make the AutoCAD design of it by measurement, and finally we built the 3D printer and printed it. We took two of the model and did that. And then with collaboration with Mahapatra in aerospace, what we have done is we have done the FEM analysis, where we try to understand what is the role of individual complexity. For example, if I take the same C-cell structure with a spherical size, what happens if you deform it? And what we see is, if you have a spherical structure, you press here, the stress or strain both distributes uniformly. The first complexity in C-cell structure, which is the this kind of spine, which results into a complexity in the surface. What we see is, because of this complexity, you see a stress localization at certain places. So it's what I mean to say is, it's not uniformly distributed. Hence, you can accommodate a lot of stress. And if you add the second level of complexity, it means these ups and downs, a positive and negative curvature, you can see it can take even higher stress level. At the same time, what another thing happens is, you can see a positive curvature and negative curvature are always opposite in stress condition. It means they can accommodate locally as well. Now, if you really want to build a structure out of it, and just to understand what really happens, because remember, all this C-cell structure, there is a living species staying inside. Now the question is it really advantageous to stay in this kind of complex shape? And the answer is, if you really want to understand, what we have done is, we take this spherical shape and put aluminum block at bottom of it. And what we are seeing here is the aluminum block and the spherical half spherical particle. When you place it, you see uniform distribution of stress. And the backside of aluminum, you have stress uniformly distributed all across. It means, suppose a species living inside here, the moment you put leg or it undergoes any stress, the living species is going to fail, is going to face a stress all over uniformly. Whereas if you add this complexity, what happens is, you see in the aluminum plate, there is a zone where there is no stress. It means if I sit here in one of the zone in this C-cell structure, and if some stress comes on top or some load is applied on top, the species will not face any stress. At the same time, if you add more complexity, you see this zone become bigger. At the same time, the localization is even diffuse. So you get more place to move around and so on. Now, this topology or this change in macroscopic scale does change with the thickness. So if it's thinner, the distribution of maximum minima is different as compared to thicker. And biologically, if you try to understand, and this is very true, if the species inside, as they grow, the thickness grows. So when it's really big, it's not very sensitive as compared to the very very younger living species. So hence they can accommodate, or they can take stress. So this changes as well. Now,
Hello, sir. Your voice is not audible. Okay, participants, there is some technical issue from sir's end, so he will be joining within couple of minutes. So please be online. The session is yet to over, so please stay tuned. Okay, I have put few names in the chat box. If they are available, please respond. Please see the chat box, and if the listed names they are available, please respond.
Yeah. Hello.
Yes, sir. Yes, sir.
Sorry for the disturbance. Yeah, there's a power cut, so I had to move to some other place. There is some repair going on. So yeah. Okay. Okay. So is the screen visible?
Yes, sir. It is visible.
Perfect. Okay. So okay. So coming back to this, so what we see is if you have this kind of topology in this kind of in this C-cell structures, we don't see what we see clearly is the stress distribution is more uniform, and there are a lot of space where there is no stress. It means if the species stays there, they are not going to feel any stress. And as I was talking about, yes, the whole thing is related with curvature, and because of this curvature, the stress difference between one point to other, or the maxima or minima, is really high as we keep on introducing more topology. And that is analytically also we do the same thing. Now, if you consider another kind of C-cell structure, which is very similar to cylindrical, if you compare with cylindrical shape, we do see if you have more complex shapes, which is shown is like C here. Just a sec. If you see the C here, you can clearly see there is a zone which is very high stress, and there is a zone which doesn't feel any stress. What it means, if the living species is going to stay in this zone, they are not going to feel any stress if you apply any load in any one of the zone. And again, this need to do with the thickness, and also it changes with the radius. So depending on the ocean condition, the morphology of both of these kind of C-cell structure can be different, just to accommodate the stress what they feel under the ocean, or also outside the environment. Also, if they undergo some impact and so on, the shape and the dimension changes just to fit into just to fit the living species in that particular condition. Now, what we have done is we started comparing, if you assume solid polymer versus and a solid ceramic versus topology engineered this complex shape. And what we see is if you have a solid ceramic, which is calcium based here, or a solid polymer, this is the stress level you can achieve in that given surface area. But because of topology, we see a huge enhancement. At the same time, when they fracture also, we see what exactly happens in nature can be mimicked in the 3D printed structure, and we can now understand why this whole structure or the stress concentration, what roles it plays in this kind of deformation in these complex shapes. Now we can extend the whole idea and look at different nature inspired structure. For example, we have chosen like ant structure, where if you see this ant hole, generally ants are one of the most efficient species on this planet Earth, because they can really take load multiple times higher than what is their of their own weight. Now, if you consider their house, when they make a hole, they're very complex, and some of the structures which is already done, and what people generally do is they pour metal into it, and the metal flows into these holes, and finally they take out this whole block and they can get the 3D structure. You can see this structure is really complex. Now the question, we want to understand what really advantage and guess making this kind of structure. So what we have done some experiment on that. We took cement and filled with this pore structure, and then did 3D scan and got the structure, and then we started building understanding about deformation and the complexity and the advantages because of this complexity. And all these things is one of the direction where we are working on. We are trying to correlate this finite element methods and the real experimental deformation, and try to understand the whole thing. Now, extending this whole idea at atomic scale. Now, if you look at carbon nanotubes, they do have a solid, nanotube. At the same time, they form this kind of interconnect junction. Now, when you do in situ indentation, where you try to indent locally, we can clearly see these kind of junctions does play an important role in terms of improving strength and their stiffness. And the whole, the reason for this kind of enhancement is given to the curvature of this junction. and we can clearly see if you have a positive and negative curvature next to each other, they can complement each other, and as a result we can get enhancement as compared to cylindrical pristine nanotubes. Now, taking this whole idea, there is a very complex structure which is already there in literature, which is called swordzites. Again, this was it was developed by a mathematician named Swartz in 1880s, and what he has done is he has created this kind of complex topology. Now, if you look at these topologies, and I have not played the video, but you can clearly see these are different structure, and what you see here is there is no point in the structure which is flat. So every point in this three-dimensional structure is curved. And you can see they're so complex, there is no method you can make it. But as these are generated in computer, we can easily print them. And this is what is shown here. This is the computer generated. We make SolidWorks structure here and then print them. And what we see here is when we do mechanical testing, we can see we can enhance the mechanical properties of the polymer by multifold. And we can tune the shape and size and dimension. All these can be done, and we can get specific strength much higher as compared to the pristine polymer. So that's another direction we are trying to explore what can be done. Now, another area of research is, if you look at the army, right? So there are several of these kind of helmets available in defense. Generally, they call it bulletproof helmets, but the problem is they're made of mostly metals and some of the composites. But the moment a bullet hits this kind of helmet, although the bullet cannot penetrate through, but what it happens, there are several studies which clearly shows that it does affect it does impact the brain of the soldier, and not in short term, but some of the cases long term also they do see some huge effect in the nervous system of the soldiers. Now, the question is, can we build this kind of porous material for such kind of application? And the answer is yes. If you take a little bit more complex structure, and then which is called tubulin here, and they are fairly dense so that they can penetrate the bullet. And these are very complex, very similar to swordzite. They are topologically complex, and they don't have any single flat surface. They are all curved all over. And once we created the structure, we have printed it, and again it shows a lot of excitement in terms of mechanical deformation. For example, there are directional, so it means that you can control the deformation depending on the requirement. Even the fracturing takes place in certain direction and so on. All these can be tuned in the structure. And you see here, specific energy absorption is way higher than just solid 3D cube, almost like twice of this. Hence, and at the same time, the density is also low. So it's lightweight. At the same time, it can absorb a lot of energy. And yeah, this is the mechanical property we are talking about. You can see it can take a lot of load as compared to any other porous structure. And most interesting is this bullet test. So what we do is you use 5 kilometer per second bullets to hit this structure. And then after the impacting, we have done X-ray imaging just to understand the cracks and so on. And if you see the structure here shown by the laser pointer, you can see if you take a solid block and you impact, you can see a lot of cracks generated. What it means the bullet has transferred all the energy till bottom, and that's the reason why you can get effect of this impact. Whereas if you make this kind of structure, you can see the bullet or energy even got trapped wherever it hits. And when we do analysis of this damage, you can see if you have a simple cube, you can see huge damage, whereas this complex structure or tubulins show almost some of the cases very less or moderate kind of damage in the structure. But one thing is clear, you don't see any energy transform or any deformation in the lower part of the structure. It means if your soldier head is in this region, it's completely protected. Now, when we do simulation, just to understand what happens, and what clearly we see in MD simulation is, if you hit the structure into this topology, and you can clearly see the bullet get trapped because of topology. At the same time, locally this structure or polymer can melt, but it doesn't transfer all the heat because it's a bad conductor of heat. It melts locally. Still, it doesn't allow the crack to propagate, and the bullet doesn't affect the lower part of the structure. And we have done detailed study in this structure, which is shown in the figures, and the details are mentioned in the paper. And this was in the cover page already. And this whole idea has been, there are people who started making the real helmets or real protection shield out of these structures already. Now, another area where this 3D printed structure with higher surface area can be used for society aspect, which is like
There are several people have shown 3D printed structure can be used for removal of contaminants or water purification or even catalysis. There are several papers. These structures are already people have started using or exploring such application. Now, this kind of porous structure, another area, can be damage tolerant, at the same time fairly controlled deformation, we can say, in automotive industry. And if you look at front part of your car, generally they are made of this kind of panel, right? So when you hit when the car hits a solid object or any object which is stronger than it than the this particular material, they deform, and they mostly they rupture or they fracture or disintegrate, but they never transfer the load to the rest of the body of the car, especially the engine part and which is attached in the front. So the another area, these are made of plastic. We started looking at can we build a structure which can be controlled deformation. And one of the work which was done by Weismuller in 2008, what they have done is they take gold and copper nano material, mix them and make a structure out of it, and then they dissolve one of it, mostly copper. They etch out the copper, and what left out is a very complex structure. Now these are at atomic scale. We are talking about 100 nanometer range. Now, and each of these blocks are, say, a couple of nanometers, and the TM shows around there like 20 to 50 nanometer. The idea is, now we have a solid structure. Can we take this atomic scale structure and try to see we get advantage of this topology at higher scale? And when we print different thickness, different density, and we can see with the density, the modulus and the strength can be tuned. Not just that, we can fit with the model, and we can get, if you say, and if some requirement comes in particular region of particular modulus, we can print that particular density material wherever you need. And not just that, we can increase surface area by making higher thickness of the structure. Hence we can have a different load bearing capabilities, as also we can have different energy absorption and so on. Apart from that, these deformations are different in different regions, and you can see if you have a coarser structure, the load transfer is fairly high, whereas if you have a fine or more surface area structure, the load transfer is localized. Apart from that, what we can do is we can build the 3D structure, or we have built the 3D structure with different gradient. When I say different gradient, means you can have a finer, coarser, or higher dense, lower dense. All these you can tune and print in a single object, and you can decide how much stress or how much load you want to take in that particular region. All these can be done with this particular structure. And we have extended some more structures where we can pick up zeolite and try to reinforce and try to understand deformation, or try to introduce anisotropy in this kind of deformation. Suppose you want just deformation in one direction, we can build those structures. For example, zeolite is one where it's very strong in one direction, another direction is soft, and it will disintegrate. Recently, we just published this paper in where we use mathematical based model to build the structures, which is called Munger sponge. They are porous, but they have certain periodicity. When we change the shape of this porosity or this individual holes, we can see we can clearly engineer the mechanical properties or energy absorption. We do a deformation of these structures and try to understand the role of this porosity or this topology, and try to compare with FEM and explain the whole idea. Apart from this 3D printing, we do work on 2D materials and new 2D materials, and try to engineer them for specific application, and most of the details are there on the website. We do work on nanoparticles and development of nanoparticles, and some of the cases we do make multi-component nanoparticles and try to see its utility in energy and so on. So that's another area our group works on. And some of these, these processes are used for environmental application like electronic waste recycling and so on, which is there in the website. And a major part of the group we do work in alloy development, where we try to engineer microstructure to get its mechanical or any other functional properties as well. There are several of intermetallic based material of higher strength or higher temperature stability. We do try to develop and try to evaluate or correlate its structure property correlation. And with that, I'll end my talk. And this is my email ID. Anyone of you have any question or anything you want to know, you can drop me an email. With that, thank you. Yeah, so you can ask the question if anyone has any question.
Participants, if you have any query, you can go ahead, unmute yourself and ask. Else, you can put it in the chat box.
Okay, I hope the talk was informative, and I
Yes,
think
I don't
yeah.
think there is any query from their side.
Okay, perfect. That's the
So
best
we
thing can happen.
wind up it here.
Okay, perfect. Thank you, guys. Thank you all. Sorry for the trouble in between, but yeah, we are living in a current technology where we have very little control on things. Some of the things, yes, can fail, but yeah, feel free to reach me. Yeah, go ahead.
Sir, we gratefully appreciate your effort and putting forward your expertise for this particular FDP, particularly responding to our invitation and kindly agreeing to deliver a talk in this particular FDP. So I thank you once again on behalf of our Department of Production Engineering, BSSDOT, and we look forward for future collaborative works and as well as to such interaction in future as well.
Perfect.
So I'll be sharing your email ID with the participants also. So when if they need it, they can get in touch with you, sir. So
perfect. And
I'll be sharing your email ID with them.
Right. Thank you all. And I do see a lot of messages here. And yeah, thank you, Rajesh. Thank you, Shandeep. Thank you, Venugopal. And thank you all. Thank you, guys. Bye-bye.
Thank you, sir. Thank you.